Our dynamic universe. The key areas covered will be the Doppler effect observed in sound and light, the Doppler effect causing shifts in wavelengths of sound and light, the light from objects moving away from us shifting to longer wavelengths, the redshift of a galaxy, and the redshift in slow-moving galaxies. What we will do today is describe how the Doppler effect affects light, to state what is meant by redshift, and carry out calculations on the above. Redshift. We're going to watch a short video by Brian Cox about redshift.
Our only contact with the distant stars is their light that's journeyed across the universe to reach us, and encoded in that light is the key to understanding what the universe is made of. And it's all down to a particular property of the chemical elements. You see, when you heat the elements, when you burn them, then they give off light, and each element gives off its own unique set of colours. So this is strontium, and it burns with a beautiful red colour. Sodium is yellow. Potassium is lilac. And copper is blue. Each element has its own characteristic colour. It's this property that tells us what the stars are made of. But it's a little more complicated than simply looking at the colour of the light that each star emits. You can see why by looking at the light from our nearest star, the Sun. This is a spectrum of the light taken from our Sun, and at first glance it looks very familiar. It looks like a stretched out rainbow, because that's exactly what a rainbow is. It's the spectrum of the light from the Sun in the sky. But if you look a bit more closely, then you see that this spectrum is covered in black lines. These are called absorption lines. Each element within our Sun not only emits light of a certain colour, it also absorbs light of the same colour. By looking for these black lines in the Sun's light, we can simply read off a list of its constituent elements, like a barcode. For example, these two black lines in the yellow bit of the spectrum, sodium, you can see iron. Right down here, you can see hydrogen. So by looking at these lines in precise detail, you can work out exactly what elements are present in the Sun. And it turns out that that's about 70% hydrogen, 28% helium, and 2% the rest. And you can do this not only for the Sun, but for any of the stars you can see in the sky, and you can measure exactly what they're made of. So that star there is Polaris, the pole star, and you can see that because all the other stars in the night sky appear to rotate around it. Now it's 430 light years away. But we know just by looking at the light that it has about the same heavy element abundance as our Sun. But it's got markedly less carbon and a lot more nitrogen. And the same applies for other stars. Vega, the second brightest star in the northern sky, has only about a third of the metal content of our Sun. Whereas other stars are metal heavy. Sirius, the dog star, contains 3 times as much iron as the Sun. And Proxima Centauri is rich in magnesium. But although the quantities of the elements may vary, wherever we look across space, we only ever find the same 92 elements that we find on Earth.
Here's some background information. Astronomer Edwin Hubble noticed that light from distant galaxies was shifting towards the red end of the spectrum, i.e. its wavelength was increasing. White light, light from galaxies and stars, is broken up into all of the colours of the rainbow: red, orange, yellow, green, blue, indigo, and violet. Red has a longer wavelength and violet has a shorter wavelength. All the colours have different wavelengths and so different frequencies. So what is redshift? Redshift, also known as Doppler shift, is how much the frequency of light from a faraway object has moved towards the red end of the spectrum. It is a measure of how much the apparent wavelength of light has been increased. It has the symbol Z and can be calculated using the following equation. Z equals lambda O minus lambda R over lambda R. It can also be expressed as Z equals lambda O over lambda R minus 1, where lambda O is the wavelength observed and lambda R is the wavelength at rest. What's a blue shift? When we use the equation for redshift, we can sometimes end up with a negative value. This means the object is moving closer to you and said is to be blue shifted. Blue shift is a measure of how much the apparent wavelength of light has been decreased towards the blue part of the spectrum this time. Redshift and velocity. We can also work out the redshift if we know the velocity that the body is moving at for slow-moving galaxies. We use the equation Z equals V over C, where V is the velocity of the galaxy and C is the speed of light. Wavelengths. With a redshift moving away, the wavelength increases. With a blue shift moving towards, the wavelength decreases.
Imagine a place where the speed of light isn't its true value of 300,000 kilometers a second, but something a lot less. Let's say 40 kilometers an hour, and strictly enforced.
Just as in the real world, we can never reach the speed of light. The commandment here is still, thou shalt not travel faster than light. But we can do thought experiments on what happens near the speed of light. Here, 40 kilometers an hour, the speed of a motor scooter. Paolo says goodbye to his little brother Vincenzo.
Ciao, Vincenzo.
And rides off. He's now going more than half the speed of light. He's almost catching up with his own light waves. This compresses the light waves in front of him, and his image becomes blue. The shorter wavelength is what makes blue light waves blue. Also, Paolo becomes skinny in the direction of motion. This isn't just some optical illusion. It really happens when you travel near the speed of light. As he roars away, he leaves his own light waves stretched out behind him. Long light waves are red. We say that his receding image is red-shifted. Now, Paolo leaves for a short tour of the countryside. He experiences something even stranger. Everything he can see is squeezed into a moving window just ahead of him. Blue-shifted at the center, red-shifted at the edges. To a passerby, Paolo appears blue-shifted when approaching, red-shifted when receding. But to him, the entire world is both coming and going at nearly the speed of light. Roadside houses and trees that he's already gone past still appear to him at the edge of his forward field of view, but distorted and red-shifted. When he slows down, everything again looks normal. Only very close to the speed of light does the visible world get squeezed into a kind of tunnel. You would really see these distortions if you could travel near the speed of light. Someday, perhaps, interstellar navigators will take their bearings on stars behind them, whose images have all crowded together on the forward view screen. The most bizarre aspect of traveling near the speed of light is that time slows down. All clocks, mechanical and biological, tick more slowly near the speed of light. But stationary clocks tick at their usual rate. If we travel close to light speed, we age more slowly than those we left behind. Paolo's watch and his internal sense of time show that he's been gone from his friends for only a few minutes. But from their point of view, he has been away for many decades. His friends have grown up, moved on, and died. And his younger brother has been patiently waiting for him all this time. The two brothers experience the paradox of time dilation. They've encountered Einstein's special relativity.
Any chance?
This was just a thought experiment, but atomic particles traveling near the speed of light do decay more slowly than stationary particles. As strange and counterintuitive as it seems, time dilation is a law of nature.
Traveling close to the speed of light is a kind of elixir of life. Because time slows down close to the speed of light, special relativity provides us with a means of going to the stars.
Light from a distant galaxy is found to contain the spectral lines of hydrogen. The light causing one of these lines has an observed or measured wavelength of 466 nanometers. When the same line is observed at rest from a hydrogen source on Earth, it has a wavelength of 434 nanometers. A. Calculate the Doppler shift, Z, for this galaxy. B. Calculate the speed at which the galaxy is moving relative to Earth. And C. In which direction, towards or away from Earth, is the galaxy moving? Let's try A first. Let's write down what we know and what we don't know. Our observed wavelength is 466 nanometers. Our wavelength at rest is 434 nanometers. So let's put this into our equation. We've got Z equals lambda O minus lambda R over lambda R. So that's 466 minus 434 over 434. This gives us an answer of 0.074. Question B. Calculate the speed at which the galaxy is moving relative to Earth. The equation we need to use for this is Z equals V over C. We just worked out our Z, so we can put that into our equation, 0.074. We don't know our V, and C is our speed of light, so that's 3 times 10 to the power of 8. So rearranging this equation, we get V equaling 2.21 times 10 to the power of 7 meters per second. Question C. In which direction, towards or away from the Earth, is the galaxy moving? Z is positive, therefore the galaxy is moving away. A distant star is travelling directly away from the Earth at a speed of 2.4 times 10 to the 7 meters per second. A. Calculate the value of Z for this star. We want to calculate the value of Z, and we've been given a speed, so we can use Z equals V over C. Our speed is 2.4 times 10 to the 7, and C is 3 times 10 to the 8. This gives us a value of 0.08. Part B. A hydrogen line in the spectrum of light from the star is measured to be 443 nanometers. So this is our observed wavelength. Calculate the wavelength of this line when it is observed from a hydrogen source on the Earth. So that is our rest wavelength, because our hydrogen source is not moving. We want to use our equation Z equals lambda O over lambda O minus lambda R all over lambda R. However, this has got 2 lambda R's in it. We want just one of these, and we know we can rewrite this equation as lambda O over lambda R minus 1. This is the equation we want to use, this second one. So putting in our values, we have 0.08, that's our Z, equals 443 over lambda R minus 1. Rearranging this, we want to add 1 to both sides, so we've got 1.08 equals 443 over lambda R. So rearranging that again, we've got lambda R equals 410 nanometers. An astronomer observes the spectrum of light from a star. The spectrum contains the emission lines for hydrogen. The astronomer compares this spectrum with the spectrum from a hydrogen lamp. The line which has a wavelength of 656 nanometers from the lamp is found to be shifted to 663 nanometers in the spectrum of the star. What is the redshift of this light from the star? So again, let's write down what we have and what we don't have. Our observed wavelength is going to be the 663 nanometers. And our rest wavelength from our hydrogen lamp is 656 nanometers. Using our equation, Z equals lambda O minus lambda R over lambda R, we can fill our numbers in. That's 663 minus 656 all over 656. Popping that into a calculator, we get 0.011. That is answer A. Accurate measurements of the wavelength of the hydrogen alpha line on Earth have determined it to be 656.28 nanometers. The graph shows how the wavelength of the hydrogen alpha line for one of the stars in a binary pair varies with time, as observed on Earth. We can see this graph here. It's plotting wavelength in nanometers against time in days. Using the information from the graph, 1. Determine the period of orbit of this star. 2. Calculate the maximum recessional velocity of the star. And 3. Explain how the maximum approach velocity of the star compares to its maximum recessional velocity. First, let's determine the period of orbit of this star. We know that the period of a wave is the time it takes for one wave to pass a point. So let's find the time for one wave. If we look at this peak up here, this is at 4 days. And if we look at this second peak, that is at 16 days. The period is going to be 16 take away 4, so that's 12 days for one wave. The second part of the question asks us to calculate the maximum recessional velocity of the star. If we look onto our graph, we can find at the first peak, the maximum velocity is going to be at this maximum wavelength just here. So looking at our scale, we can work out that this is 656.41 nanometers. That is going to be our observed wavelength. Our wavelength at rest is where they tell us at the top of the question. That's 656.28 nanometers. And we can now use our equation to work out Z. I'm going to write it as this. It's much easier to put in our numbers this way, just in a calculator. You can use either equation. They'll both give you the same answer. So if we say Z is 656.41 over 656.28, take away 1 from that, we get an answer of Z being 1.98 times 10 to the negative 4. But we're not finished yet. We need to calculate the maximum recessional velocity. So we need to use Z equals V over C. We've got our Z, it's 1.98 times 10 to the negative 4. That equals V over 3 times 10 to the 8. And I'm just about running out of space. I'll put it up here. So if we grab our calculator, we get 3 times 10 to the 8 times 1.9 times 10 to the negative 4. And we get an answer of V equals 59,400 meters per second. Part 3 asks us to explain how the maximum approach velocity of the star compares to its maximum recessional velocity. If we have a quick look on the graph, we've already worked out that our point just here, that's the maximum recessional velocity, with 656.41 nanometers. If we look at the trough instead of the peak, just here, we can see that is 656.19 nanometers. This trough relates to the maximum approach wavelength just there. So let's write down a few numbers here. We've got the maximum recessional wavelength equals 656.41. We've got the maximum approach velocity, not velocity, just the wavelength at the moment, is 656.19. And we have our rest wavelength. That's given at the start of the question. That was 656.28. Comparing our maximums to our rest, we can see that our maximum approach wavelength has a smaller difference to the rest than the maximum recessional wavelength. So there's a smaller difference between the maximum approach wavelength and the rest wavelength. Therefore, our blue shift, this is relating to approach, is less than our red shift. And our approach velocity is going to be less. So that's our final answer there. Approach velocity is going to be less. And that's than the recessional velocity. The diagram below represents part of the emission spectra for the element hydrogen. We can see we've got increasing wavelength from left to right, and spectrum P is from a laboratory source, and spectrum Q shows the equivalent lines from a distant star as observed on Earth. 1. Explain why spectrum Q is redshifted. Initially, you need to say that the star is moving away from the Earth. That'll get you 1 mark. Then you need to mention something to do with the wavelength or the frequency, increasing or decreasing, and maybe even Doppler shift or redshift. So any of the following points would get you the 2nd mark. The apparent wavelength of the hydrogen spectra from the star has increased. The apparent frequency of the hydrogen spectra from the star is less than the actual frequency on Earth. The frequency of the light from the star has shifted towards the red end of the spectrum, or light from the star is experiencing a Doppler shift. Question 2. One of the lines in spectrum P has a wavelength of 656 nanometers. The equivalent line in spectrum Q is measured to have a wavelength of 676 nanometers. Calculate the recessional velocity of the star. So we know to calculate the velocity, we want to use the equation z equals v over c, but we don't have z yet. So we want to use the equation z equals our observed wavelength over our rest wavelength minus 1. But which one is our observed wavelength and which one is our rest wavelength? Well, our observed wavelength is the 676 nanometers because that's from spectrum Q, that's of the star itself. And our rest wavelength is 656 nanometers because that's spectrum P and that's a laboratory source which is not moving. So let's pop those into our equation. Z equals 676 over 656 minus 1, and that gives us an answer of 0.03. Now we can put that into our other equation. We've got 0.03. In fact, let's write our equation first. Z equals V over C. We've got 0.03 equals V over 3 times 10 to the 8. Rearranging that, we get V equals 9 times 10 to the 6 meters per second. Watch out! You must be careful with the wording of some questions when deciding which wavelength is the observed and which is at rest. It can be confusing. A galaxy is moving away from the Earth at a velocity of 1.2 times 10 to the 7 meters per second. Light of wavelength 450 nanometers is emitted from this galaxy. When detected and measured on Earth, this light has a wavelength of, and that's what we want to work out. So, what is this question actually asking for? It's asking for lambda O, the observed wavelength. So let's write that down. We want to know what our observed wavelength is on Earth from the galaxy. The 450 nanometers is emitted from the galaxy, therefore that's our rest value. That's at the galaxy, it is emitted at 450 nanometers. By the time that this 450 nanometers reaches the Earth, it will have shifted, so that's what we're going to work out. We can use our 2 lambda values to work out Z, but we don't have one of our lambda values, we need to work out z first. Z equals v over c. Our velocity is 1.2 times 10 to the 7 divided by our speed of light. And for that we get a value of 0.04. Now we can use z equals lambda O lambda r minus 1. We can say 0.04 equals our lambda O over our lambda r is 450 minus 1 from that. So we add on 1 to both sides. We've got 1.04 equals lambda O over 450. Rearranging this, we get lambda O, or our observed wavelength, is 468 nanometers. This corresponds to an answer of C.